All right, we hopefully should be live for Worldcon office hours. Let me just double check. I think we are. Office hours. Yep, we are. We are live. Sorry for that little delay here, but I'm using a backup. I'm using a spare laptop today because my main laptop had troubles booting up this morning. So if it looks a little different, my screen is because I am using a different laptop today. Had some boot up issues. Sorry, we're starting a little 2 hours late today, given some other prior things that took a little bit of precedent. But let's go ahead and move on. Let's go ahead and start with office hours. I can rename this to office hours 23, I believe. 23. And today's date. All right, see Esau is here. Welcome back, Esau. What we're going to go ahead and do is we're going to pick up where we left off with our discussion with TensorFlow. As a recap of what we did yesterday is that we finally were able to build our very first neural network model. Right, it took several days for us to get to there, but hopefully we had good conversations about what are neural networks, what is deep learning, what's going on with TensorFlow and the philosophy behind it, and we built our very first neural network model. I see Mickey Rat is here, Dara J is here. Welcome back everyone for office hours. And we said that this idea of Keras, where we have TensorFlow, and Keras is a API for us to easily work with TensorFlow. So we can go through the history of Keras, so it's sort of a third-party library, a third-party package that will provide a standardization-based way to work with neural network frameworks, and now it's been officially adopted by Google, by the TensorFlow project. See, Suleiman is here. When I say API, keep in mind that API is a rather generic term. API means application program interface. Basically a set of rules or procedures one would use to interact with a program. What's sort of a little bit confusing with that phrase, and I know I was confused at when I first learned this stuff here, is that there are web APIs. We talked about web APIs in Unit 1, and because web APIs are rather ubiquitous, some people just simply shorten them to APIs. So working with the web, we work with web APIs, and people don't want to say web API all the time, so they simply just cut it off as API. But API is just a generic term. We talk about the scikit-learn API, the Pandas API, and now we're talking about the Keras API, a nice application program interface for us to easily construct these neural network models. And let's go ahead and reconstruct what we did the other day. Let's go and reconstruct what we did the other day. So let's go ahead and say from, I think, what was it? From TensorFlow. I should probably download. I'm using a different laptop these days, unfortunately. Well, not these days, today, because of some issues. So give me a sec while I'll go ahead and download our previous notebook. So this is what we had before, and I'm just want to go ahead and just copy and paste some stuff, so it's a little less stuff for me to write. First thing I'm going to do, we're going to load up our data set. And remember yesterday let's see, I get an error message. Oh, come on, I get an error message. What could be going on? Already exists. Another metric already exists. Let's see what. Fashion MNIST. Of course, then it's name error. You do kernel, restart and clear output. Maybe that would. So run all. Now I get an error. Another metric already with that same name exists. So let me go ahead and copy that and say keras. Please never import twice. Okay. So this is please never import twice. Let's see what I do there. Kernel. Restart. I still get that same error. Well, that's unfortunate. That is unfortunate. Oh well. Oh well. I can't load the data set. That's unfortunate. Let me see. Let me try to debug it one more time. It's probably a bug, right? Important bug. Oh well, it looks like we just can't use that data set. Let's see if I can use the mnist data in scikit-learn. So I do need to install scikit-learn in my virtual environment. So give me a sec while I set that up. Source. Type in here, mnist scikit-learn. It's in low digits, so import dataset and low digits. All right. I'm going to do kernel, restart and clear output. And that's unfortunate that for some reason I cannot load up the mnist dataset, but we'll go ahead and use a different dataset. We'll use the traditional or the original mnist dataset. So from sklearn, import sklearn datasets, import load digits. Load digits. And we can say data equals load digits. Does it really end in an underscore? It's a little weird. All right, and then let's go ahead and pull out the train test split. So x data, y equals data, target, and from sklearn, model selection, import, train test split, x train, x test, y train, y test, train test split, x, y, test size to be 20%, and a random state to be 0, so we have reproducible results. And yesterday we saw the API to construct our model. The first thing we did is we create a model object. The thing about using a different laptop than we're used to is the keyboard is slightly different, so that's a little bit of a trip up for me. And I get a model that already exists, so something is going on with my installation of scikit-learn, of TensorFlow. Oh well, we'll have to proceed. Things like this happen. So I'm going to go ahead and run things without things really working. So what I can do is there's an alternate way. Well, actually, let's write out everything what we had before. We had all this thing here. We added the layers. And notice how we added the layers one by one by one. Now that's a little tedious. That's a little tedious, adding layers one by one by one. There's actually a different way we could have constructed our model. And that would have been saying model equals keras, model sequential, and then give it a list of steps, a list of layers. So this would have been an alternate way I could have constructed my model. Layers, flatten, input shape equals 28 and 28. Keras, layers, dense, 100, activation, sigmoid, keras, layers, dense, 100, activation, sigmoid, and then finally keras, layers, dense 10, activation, softmax. This here is an alternative. Let me blow this up. It's a little easier to read. An alternative to what we saw yesterday. A different way to use the sequential API. The reason I'm showing you this alternate way is because I prefer this one here. I'll let you decide which one you like better. But I like this here. I like this alternative way. The reason being is I see everything all at one place. I'm not calling add multiple times. I specify the layers upon the creation of the model. And not only that, but this resembles a lot like a scikit-learn pipeline. Wouldn't you agree that if you take a look at this, this kind of looks like how I create a pipeline in scikit-learn? That's great. And we talked about previously in last week, you can view that each layer is sort of a step in our pipeline. And we see that symmetry, or see that resemblance here when we use the sequential API. So we created our model. And the one thing I wanted to show you, but I can't because for some reason it's not working for me now, is that when we call fit, we give it the data set, X train, Y train. We choose the number of epochs, and we choose a validation split, or we can specify a validation split. But actually, before we fit it, we have to compile, or we got to compile. Input shape, not shap. All right, thank you, Renato. So first thing you compile. And when we compile, we say, what is the loss? What is the loss function we use? Sparse, categorical, cross entropy. We are also going to specify any metrics to show, for example, accuracy, besides log loss or cross entropy, which is hard to kind of understand what that is, right? If you tell me this is the model's log loss, it's hard for me to interpret what that means exactly. Accuracy is something I can better interpret, better understand what's going on. And then I specify an activation function, right? An optimizer. Optimizer, for example, SGD. And then I can fit my model. It's the same thing we did yesterday. The reason I'm going through this here is for us to be reminded about all the different design choices, all the different things I can choose to modify my model. Because we want to spend some time today going through all those pieces and talking about how do you choose it. And the input shape is 28 by 28. A little typo there. I'm not going to be able to run this because it's not working, but oh well. All right, so we would call model fit to get it to start training. And we're going to run it here for 30 epochs. And remember what is happening. For these neural networks, they're trained using some form of gradient descent and some sort of batch gradient descent. In other words, we have the entire training data, but we don't use the entire training data at once to estimate the gradient. We estimate the gradient using batches of my data. And as I go through one pass of my data, taking batch by batch by batch, that is one epoch. And I'm setting to 30 epochs. Does the sequential API imply that there's also a parallel API? Would it work without flattening? The sequential API implies that there is an alternate API called the functional API. And there, so yes, as you pick up Ramsey, there's going to be some situations where we want to have some parallel and some branching. A little more complicated workflow. The sequential API is for the outputs of one layer all go directly to the next layer. However, what if we want to send some of these outputs to a parallel step? So that other API, it's not called the parallel API, but it's called the functional API. And I do want to spend some time talking about that functional API. So your intuition is correct there, Ramsey. Anything else we want to bring up before I keep on moving on? Let's see if I can go ahead and try to fix my virtual environment. Okay, I'm going to move on. So in scikit-learn, when I call fit on my model, I've fitted my model. I've mutated its state. Now I have a trained model. But in TensorFlow, so go back to scikit-learn. If I were to call fit again on that model, then the model loses its state. I'm training the model from scratch. So in scikit-learn, when I create a model, when I fit that model, and I call fit again on that same model, it starts from scratch. The training begins anew. And the reason why is because in scikit-learn, models fit is not the method you call if you have an online learning model. As you recall, I'm not sure if you've seen those videos yet. I forget where it is in the syllabus, but an online learning model is one that you can keep on training, keep on fitting. So you train an initial batch of data, initial data set, and you can continuously update the model state by giving it new data. Models that can do that are called online learning models. And in scikit-learn, in order to have an online learning model, in order to invoke online learning, you call partial fit method instead. You first call fit, and then you subsequently call partial fit. So in scikit-learn, you call partial fit to pick up the training where you left off. However, this only works for models that are capable of online learning, which not all models are capable of, by the way. Tree-based models are incapable of online learning. In general, models that rely on an iterative process to solve for model parameters can be used for online learning. All right, so we saw how in scikit-learn called partial fit for online learning. The reason I'm talking about this here is because in TensorFlow, or just in general, neural networks are capable of online learning. So neural networks are capable of online learning because they use an iterative scheme, gradient descent, to solve for model parameters. Can you explain the difference between partial fit and warm start? Warm start says, let's see. Warm start is sort of a very specialized type of partial fit. Warm start, problem is warm start is a generic term, but I'm guessing what you mean by there is warm start type, a keyword in a random forest in scikit-learn. And that's the case, then the warm start says go ahead and add another tree or add n more trees into our forest. So it's kind of like online learning. However, you're simply adding more trees. You're not affecting the other trees. So it's a little bit more specialized online learning if you're referring to warm start in the context of a random forest. Because warm start is one of those terms that is just used quite often. But yes, partial fit. So there are models that are capable of online learning. You can tweak them without using the original data. You can just tweak them using just the new data. I'm not sure if we've seen those videos or have we posted those videos. SGZ also has a warm start option. Okay, so that probably, right? So when you say SGZ, you got to be a little more specific. You refer to scikit-learn, stochastic gradient descent regressor. Let's take a look at the documentation. Warm start. When true, reuse the solution in the previous call to fit as an initialization. Otherwise, just erase the previous solution. Repeated calls to fit and partial fit when warm start is set to true can result in different solutions than when calling fit a single time because the way the data is shuffled. If a dynamic learning rate is used, the learning rate is adopted depending on the number of samples already seen. Calling fit resets the counter when partial fit will result in increasing the existing counter. So you are correct that the SGZ regressor does have a warm start, a keyword. If I see the glossary here, let's see how they're defining warm start. When fitting an estimator repeatedly on the same data set, but for multiple parameter values, such as find maximum performance in a grid search, it may be possible to reuse aspects of the model learned from the previous parameter value, saving time. When warm start is true, the existing fitted model attributes are used to initialize a new model in a subsequent call to fit. Note that the only application for some models and some parameters are some parameter values. For example, warm start may be used when building a random forest to add more trees, kind of like what I said. Partial fit also retrains the models between calls, but differs with warm start. The parameters change. The data is more or less constant across fits. With partial fit, mini batch or data changes and model parameters stay fixed. There are classes when you want to use warm start to fit differently, but closely related data, for example. Okay, so not to spend too much time on it, but scikit-learn does a good job explaining the differences and what they mean by partial fit and warm start. So do take a look at that in the glossary of terms. Don't want to spend too much time talking about that. But scikit-learn once again comes through with some good documentation differentiating between what they refer to warm start as opposed to partial fit. But nonetheless, the point I wanted to come across is that neural networks are automatically capable of online learning. In other words, we can train the model with, let's say, 30 epochs. And if we're not satisfied with the results, then we can call fit again. But when we call fit again, we don't lose our work. We just pick up where we left off. And you can think of the training process is continuously trying to improve the model. So instead of starting from scratch, we pick off where we left off. So calling subsequent calls to fit is not going to start from scratch. We're going to start off where we left off. So unfortunately I can't do that. Actually, I'm trying to reinstall TensorFlow. And let's see if that fixes things. Okay. So running that would have to wait. Now let's kind of let's keep track of all the design choices we have. Well, at the very top, it's how many layers? Right? How many layers? We also get to choose, or we have access to how many neurons in a layer. The activation function. We can choose, let's see, the optimizer. We can choose number of epochs. We can also choose the batch size. We can also choose how we initialize our starting model parameters. And what else? What other things did we go through our discussion said, okay, that's something we can choose and design on. Let's go put a pin on that. How many layers? How many neurons in a layer? The activation function, the optimizer, the number of epochs, the batch size, and how we've initialized those weights. I think that's most of them. There's probably some other ones I am forgetting, but I think this is a good start. Notice how just right now there are over 7 different design choices. And they also very much affect each other, right? How many layers? How many neurons in a layer, right? That's just so much ranges of values we can choose from. So let's go through some of these and figure out and talk about how we best choose them. I think what we'll do is we'll choose the easy ones. We'll choose the easy ones first. So, how about the batch size? The batch size. In other words, how many observations should belong in a batch that make up one training cycle or one training run? Well, typically there's been some studies and reports suggest that you should use probably 32 observations. 32 observations, but not that big of a deal. I believe the default in TensorFlow is 32. Okay. So that's pretty easy, the batch size. Then what about how we initialize our starting model parameters? And remember, in any type of iterative scheme or iterative algorithm, we need to have a starting point. We need to say, okay, we're going to start at this value, and then we apply gradient descent to continuously tweak where we are. And I won't go into the math right now, or I won't go into the math here at all, but if you start your model parameters all at the same value, then you're going to have a symmetric system. In other words, the weights are going to be symmetric. You're going to have same weight values for every layer, or something like that. That is not a behavior, not an outcome we want. So typically we have to start with random values for these weights. However, in any type of gradient or in any type of iterative search, where we start has a great effect on where we end up. Where we start in our search greatly affects where we end up. And that's going to greatly affect how long I need to train the algorithm for. That kind of makes sense, right? Where I start affects my final answer. And if I can start at a better place, then that will take less training runs or less training time to get a good model. So there's a whole area of research that goes into figuring out how to best initialize the model weights. I can choose what those are, but it's best to stick to the default in TensorFlow. So I call that an easy one because, well, we just stick to the default. And now my browser is frozen, or now my computer seems to be frozen. So much technical issues today. Okay, let's see. If I do kernel, restart and clear output, I'm kind of curious to see if... Give me a sec. Got a dead kernel. Kernel, restart and clear output. I've reinstalled TensorFlow. Let's see if this ends up working. Okay. All right, let's see if this works. So run on above. Maybe I got a different error now. Ah, yes. Fixed it. Now I can download. Now I got TensorFlow to work. Now I can actually run these cells. All right, create the sequential API. I can do it the alternate way. And let's go ahead and train. Attribute my TensorFlow curves has no model. What is it? I messed up. Models. Plural. All right. So that's training. I'll go and move on, talk about our discussion here. All right. So how we initialize our parameters, just take the default. Batch size 32. Well, the question is, how many epochs? How many epochs do we do? Now, what if I say, I don't know, I'm going to do 1,000 epochs. I'm going to do 1,000 epochs. I'm going to go out for lunch. Would I run the risk of setting a very large number of epochs? And once again, when we talk about these design choices, we always go back to some fundamental discussion. So what is the risk of setting 1,000 epochs or some very large number of epochs and just going away for lunch and come back for the final answer? What I run the risk of? Why can't I just have a very large number of epochs and just forget about it? What do I run the risk of? Overfitting, exactly, right? Exactly, Anthony, right? Exactly, of overfitting. Exactly, overtraining, overfitting. That's the problem if I were to set the number of epochs to be substantially large. So I got a dilemma here where, yeah, exactly, Ramsey, overfitting. So I got this dilemma here. If I set the number of epochs to be really small, then I'm going to have a model that still needs more time training. I need, still need some time to, to bake in the oven. But if I set the number of epochs too large, and I'm not keeping an eye on it, well, then I run the risk of overfitting. So how do I go about solving this problem? I can solve this problem through a concept of early stopping. And remember what's happening here. When I train my algorithm, notice it's telling me my loss, my training loss, and my validation loss. And notice right now, there's still more training loss than validation loss. So there's still more validation loss than training loss. This tells me that I can still keep on training the model. So I could, since I have online learning, since this is automatically does online learning, I could just open up a new cell and call, using a different laptop, different keyboard, makes a big difference. Paste that right there. When I fit again, notice how my loss picks up where we left off, right? It's a little different because it's a different epoch, but notice, hey, it looks like I'm picking up where I left off. So wouldn't it be great that I can have a system that is continuously monitoring my loss and my validation loss? And maybe what the system will do is it will trigger an early stopping of my training if I start exhibiting overfitting. So in other words, if I were to sketch this out, and here's my training loss, but at the same time, I also have my validation loss. And if all of a sudden my validation loss starts to increase, right? Notice how it increased from this epoch to that epoch, the number of epochs. Then we should stop the training process. We should stop the training process and revert to our model's previous state. Why can't we just have some sort of system that is keeping track to say, oh, Are we achieving overfitting? Are we actually increasing our error, our validation error? Because that's the point, to trigger the early stopping. And the great way is that there's an easy way to do this in Keras. An easy way to do this in Keras, and that is through the system of callbacks. So let me show you how you can set up a callback in TensorFlow. So here, let's see, loss and okay. So I'm still not overfitting, but let's see how we can set up a callback. So what I'll do, use solution, use early stopping. All right, so what I'll do is I'll say early stopping is equal to Keras callbacks, early stopping, monitor the validation loss. That's what we're going to monitor. That's going to trigger whether we should have early stopping. We're going to set patience to 5. So patience mean how many epochs do we observe? How many epochs when we have increasing error before we stop the process? The reason why is because there's just going to be natural fluctuations in our model's performance, right? You know, when I draw these curves, I tend to draw them somewhat smooth, but in reality, we see them a little bit jaggedy. There's variations between epoch to epoch. So it's very much could be a case where I drop my validation loss on one epoch, and next epoch I have a slight increase. That's just a natural variation of the system. So patience says this is the number of epochs we must increase our error before we cut the process, before we end the process. So we must increase our validation loss 5 epochs in a row before we stop the process. So we're going to set a patience, right? We don't want to quit too early before just a natural fluctuation. We'll set a patience to 5. And we'll go ahead and say, all right, set that early stopping. And then what we'll do is when we say model fit, go back here. What we'll do is we'll specify callbacks, and we will say early stopping. And let me cut this here. Since I'm going to do early stopping, why not 1,000 epochs? Why not 1,000 epochs? I can do 1,000 epochs because I know my system will stop, will prematurely stop. Okay, so I'll let that go on, but it's going to stop eventually because of early stopping. So how to choose number of epochs? Use early stopping will make your life easier. Questions about early stopping before we go back to our laundry list of design choices. Is each epoch considered a new data subset? Each epoch uses the same data. So, for example, let's say I have 10,000 observations. 10,000 observations, and I set my batch size to 50. 50 for just for ease. So 10,000 divided by 50 is 1,000 over 5, which is 200. So there's 200 batches. So I can take my data set and break it up into 200 batches. As I go through each of the batches and I go through the entire data set, that's one epoch. The second epoch starts again. So it's not a different data set. It's using the same data set. It's using the same 10,000 observations every epoch. It's just the way I separate the epochs is one pass through the training data. wouldn't warm start then, which uses the same data set, work better here? I think I don't want to have a discussion about partial fit and warm start, like the intricacies between that, because that's scikit-learn, and TensorFlow doesn't deal with a distinction between warm start and partial fit. So I will leave that to the glossary term to differentiate between warm start and a partial fit. I do agree it seems they're nearly the same, but it does seem that they do indicate when to use one and when to use the other. But in TensorFlow, there is no they don't use the term warm start or partial fit at all, because in neural networks, they are all capable of online learning. So fit will just be kind of the equivalent of scikit-learn of calling partial fit. This stopped. This stopped right here. The training stopped. It didn't go to 1,000 epochs. It stopped early. It stopped early. And let's see. Right. Let's see if we can show that. That kind of makes sense. Right. The validation loss was this number here. So it increased. Notice how there were 5 epochs in a row where the validation loss failed to go below the minimum. And that's what it triggered the endpoint of the algorithm. It stopped it right there. Questions people have? Early stopping is a very quick, cheap way of preventing overfitting. It's a very crude but effective way to stop overfitting. Okay, do let me know, but I will keep on moving on. So we know how to choose the batch size, how to initialize the model weights, number of epochs, the optimizer. So does it mean that we will not get to the optimal solution of gradient descent? So what's happening here is that we don't know what the optimal solution is off the bat. These are very complicated nonlinear models. So we don't know what that optimized the best answer is. We just are looking for something that hopefully is good enough. So it's less about whether we will find the truly optimal answer in our search space, because that's nearly intractable. That is impossible to find. Our goal instead is finding a really good solution instead. So early stopping will stop the training process, but will hopefully stop the training process at a point where we've reached a pretty good solution. It's less about finding the best answer, which is impossible or intractable or nearly impossible, or theoretically possible, practically impossible, and instead trying to find a really good solution. Because finding the truly best answer requires infinite amount of time, because these are very complicated, nonlinear, high-dimensional problems. Okay. Do let me know if there are other questions. But let's talk about optimizers. So the algorithm that's being used to solve for the model weights is just a variation of gradient descent. Gradient descent on a batch of data. Now, gradient descent says that the way I adjust my weights, right, the way I adjust my weights, so the way I adjust my weights is my previous weight minus some step size alpha times the change in my loss function with respect to my weight, right? That's a fundamental equation of gradient descent. But what happens if I hit a region where my loss function doesn't change as much with the weight? What happens if I hit a very flat region of my search space? What happens to the way I update my model's weights? And all of a sudden I'm adjusting my weights and I hit a very flat region. How does that affect how I adjust my weights? If the way I adjust my weights is proportional to the derivative or the gradient, if I hit a flat region, then my weights aren't being updated as much. So what might happen is I might get stuck in a very flat region. If I get stuck in a very flat region, I may not move that far from there. So this is a problem. Because I have a very complicated nonlinear search space, I might get stuck in a local minima. Or some sort of local answer that isn't really a really great solution. So I run the risk of getting stuck in a certain place. So that means that I cannot rely on plain gradient descent. So instead, I work on a variation of gradient descent that deals with the concept of momentum. And in momentum, what ends up happening is if we do get stuck, let's say here's our search space, we are a slope and then it plateaus, and here we are. Once we hit a flat region, our acceleration is nearly zero, but we have momentum. And we have momentum that will hopefully carry us over this flat region to some lower space. So previously we would get stuck and come to a crawl. But if our optimizer has this idea of momentum, where I may not be accelerating anymore, but I have momentum that will power me through, that will hopefully prevent me from getting stuck in local minima. And this idea of momentum, there's also the idea of friction. But I can modify my optimizing algorithms to have this idea of momentum. I can also optimize these algorithms to be adaptive. In other words, modify the step size according to how things are going. Adaptive. And finally, there's one other thing I can add to these optimizing algorithms, and that's called the Nesterov trick. I won't get into the math of what this Nesterov trick says, but it says that I can get a better answer if I evaluate the gradient at not at my current position, but my current position plus where momentum would take me. So the Nesterov trick. So I can take these ideas of having momentum, adaptive learning rates, and the Nesterov trick, and then have a different variation of gradient descent. And that's called NADM. And by the way, people are always continuously researching better optimizers out there. So it might be that there might be something that people prefer besides NADM. Who knows, right? People are always trying to look to see if there's a better optimizing algorithm out there. Additional bells and whistles they can apply. The point I'm trying to get you across today, or the point you should focus on, this idea that these algorithms, these optimizers, are basically gradient descent with additional bells and whistles like momentum and adaptive learning rates. So we should probably use those. We should probably use those instead. So when it comes to optimizers, use something like ADAM or NADM. So what I can do is I can go back here when I did model compile. And I can say callbacks equals early stopping and change this to NADM. And let's choose, I don't know, 200 epochs. Why not? 200 epochs. And let's go ahead and train. Okay. So we talked about how many epochs, batch size, how we initialize the weights, and the optimizer we use. Questions people have about the optimizer piece before we go back and look at other things so we can adjust in our model. So now I hope you're getting a better appreciation that these things are complicated and we don't necessarily want to use them right away because they do involve time and investment and effort to really get them to work right. Okay, let's see how this is doing. I think this is doing better. I think this is automatically doing better. Not automatically, but it seems to be doing better than we had before. I think last time our best model had a validation accuracy about 77% at the end, and this one's already at 79% accuracy. How can EDA support model development here? By EDA, I'm assuming you refer to exploratory data analysis. Not much. Not much, to be blunt. Very little. Okay, do let me know if there are other questions. I will let this keep on training, but I'm okay with having such a large number of epochs because I have early stopping here. So let's go back and let's talk about activation function. So right now we've been using activation function of sigmoid, and sigmoid is the traditional one, the one that people started using initially. Probably because we use it for logistic regression and people romanticize neural networks, and I think the brain uses something that resembles a lot like a sigmoid. But once again, we should not romanticize and get fixated about what biology does or sort of what nature does. Not because I'm against nature, but because my point is these systems aren't necessarily how the brain works. They resemble how the brain works at a high level. But nonetheless, the activation function has a strong effect on how well the model does. And how well the model and how quickly we can converge to a set of good, really good model weights. It's right. That's the holy grail of deep learning and neural networks. We want to figure out what are the model weights we need for our problem. And it becomes how do we best search through that space, that very complicated, high-dimensional, nonlinear space. We'll go and spare all the nitty-gritty details, but the best activations function to use, or one of the best ones to use, activation function, is rectified linear unit or its variance. There are some notable exceptions. For example, when dealing with recurrent neural networks, but always use softmax activation for the output layer. So for the activation functions for everything else, we should use rectified linear unit or its variations. There are variations of rectified linear units that try to improve on some sort of deficiencies of it. Some notable exceptions. We're dealing with recurrent neural networks. It's preferred to use a different activation function. I have to think about what that is at the top of my head. But the output layer should always be softmax. Should always be softmax to normalize it and have that softmax behavior. So it looks like here we're at 79% accuracy, so a little better than last time. Then if I go back to my neural network, where I created it, I'll go and copy that there. Paste it here, and I would change sigmoid to rectified linear unit. And let me go ahead and rerun training. Let's see how much better this does. Okay, questions people have about activation function. Oh, by the way, I didn't draw what rectified linear unit looks like. But it's flat and then it's linear. And because this is just a very simple algorithm, flat in a linear space, sorry, a line, literally a line, they're quick to run. They're fast to run. There's variations. There's something called leaky with a non-zero slope here. There's exponential, which has an exponential decay in a linear phase. So this is what I mean by variations of rectified linear unit. Ooh, look at this. Look at this. My accuracies are rated at 83%. Previously, I was stuck at 79. Within 10 epochs, I'm already at 83, 85%. So notice how much choosing the activation function might affect the model weights I get. Right? All it is doing techniques that can make it a lot faster for me to come up with a really good answer. Questions people have before we wrap things up for today? Keep in mind that this is a crash course on deep learning and TensorFlow. All right, I'm doing better and better. Oh, looks like it stopped there. And now I achieved about an 85, 86% accuracy. Yeah, we went from around 75 to 85, 86. Okay. A couple things we haven't talked about is how many layers and how many neurons in the layer. So we'll talk about that tomorrow. But now, as I keep on saying, you hope you get a better appreciation of how complicated these things are and why we should only really use them when we really have to. When we cannot achieve a really good performance with those traditional ML algorithms. I probably mentioned my personal belief is that neural networks and deep learning get a little bit too much of attention because they are the impressive applications. But it's worth knowing understanding what's going on here. It's a whole other field of machine learning. All right, with that said, take care everyone, and we'll pick this up tomorrow.